Okay, so in the second part of my talk, I'm going to talk about the different technology to remove antibiotics in wastewater treatment plants. So in these slides, you will see the different technology that they use. Okay, so we're going to focus more on electrochemical oxidation or electrochemical methods and absorption using a particular material, which we call the nano material. Okay, so there are different processes to remove some chemicals in wastewater treatment plants. Unfortunately, most of these treatment methods fail to remove antibiotic resistant bacteria and antibiotic resistant genes. So, for instance, the chlorination, which everyone is familiar. Okay, chlorination was found to increase the proportion of antibiotic resistance and potentially pathogenic microorganisms. So they found out that antibiotic resistant microorganisms can survive chlorination and in turn can be introduced into drinking water system. Now, the BAC filtration, biological activated carbon, and chloramine disinfection, it enhanced the resistance of antibiotic resistant bacteria against ampicillin, rifampicin, chloramphenicol, and streptomycin. Okay? Ozone, which is used for ozonation, it can react with the organic matter and the metals that's present in the water, but it has a slight effect on antibiotic resistance bacteria and antibiotic resistance genes concentration. Okay? And the way that they look at the other treatment that they use, which is sun filtration, it just increased the relative abundance of antibiotic resistance genes, but decreased the absolute antibiotic resistance bacteria. Okay, so those are the problems of the present wastewater treatment processes that is used to remove chemicals. It cannot remove the antibiotic and its antibiotic resistant bacteria or antibiotic resistant genes. So the first study that I did is to use these nanomaterials. Okay, so if we're going to look at nanomaterials, these are small scale substances. So these are structural components that are in the range of 1 to 100 nanometer. That's why they call it nanomaterials. Okay, so since it has a very small uh, range in terms of the size, it can lead to a large surface area in relation to the volume, making them highly reactive. Okay, so nanometal oxides they are found to be helpful with the removal of pollutants in aqueous system. So this is due to the fast kinetics, the preferable absorption towards the pollutants in water, and the high absorption capacity. And there are already a lot of studies reported in literature about the use of nanomaterials. So they can use like nanos adsorbents. So it's just like the adsorption technology. So you can have nano adsorbents, okay, by using atoms of the elements with high absorption capacities. You normally use here the metal oxides, just like what we're going to share to you in this talk today. Okay, so you can also include here the activated carbon, the silica, the clay, and other composites. Now, nanomembranes, on the other hand, you can define them as filters that separates the liquids and the gases at molecular level. Living cells use nanomembranes or a form of nanomembranes to function. Okay, so these processes in biological cells includes the transfer of salts from blood and the transport of oxygen to and carbon dioxide from cell. Okay, so there are a lot of examples that already been reported about nanomembrane. So they said a nanomembrane can be seen as the only nanotechnological object that can be manipulated without the use of any special treatment. Now, nanocatalysts, on the other hand, they're just similar to catalysts. So, what do we say about catalysts? Anything that hastens the reaction. So, nanocatalysts here, the only difference is the size, and it helps speed up the reaction. So, if you're using it for environmental purposes, it helps to break down, okay, some materials. So if we have a nanocatalyst, they stand at the boundary between homogeneous and heterogeneous catalysts, in the sense that in many cases they offer advantages from both in terms of activity, selectivity, efficiency, and reusability. Okay? So some of the nanoabsorbents that has already been reported are listed here. So you can see here carbon nanotube. So that's one of the first set of nanomaterials that has been studied. So they found it to be reusable, although it's costly. Okay, its application is both in the pharmaceutical and antibiotics. They are found to be a highly accessible absorption sites. Okay, and the negative aspect to this is it has a possible health risk, and they also found it to be bactericidal. Now, the polymeric nanoabsorbent, they found it to be reusable, complex production process, that's the negative aspects, and applications removal of organics and heavy metals. It has a bifunctional for both organics and heavy metals. And then we have the zeolites, okay? So this controlled release of the nanosilver, it's bactericidal. The only negative aspect for this is reduced active surface due to immobilization, and it is used for disinfection process. Okay. Now the objective of the fourth, when we did the study on using these nanomaterials, is to monitor the binding interaction of the antibiotics with nanomaterials using instrumental methods. So we use UVBs, that's the absorbance, and spectrophlorimeter. Okay, because there's some fluorescent antibiotics that we use. Okay, and to monitor the amount that was bound that bound to the nanomaterials, we also use HPLC. And from this, we determine the potential of nanomaterials as remediating agents in the removal of antibiotics in environmental sample. So this is, we could say, all lab-based study. Okay, so you as a chemical engineer, maybe you can improve this initial study that we did, okay, and put it into a large scale application. So the material that we use, we have two tetracyclines, doxycycline and oxytetracycline, and then four sulfa. Okay, so we use this one because these are the most commonly used antibiotics. So the difference of the four sulfa, two of them, if you're going to look at them, has a 6 carbon ring compared to the other two that has a 5 membered ring, not carbon, 5 membered ring, because not all of them are carbon. So we use sulfametacin, sulfametisol, and then sulfadiazine and sulfamethoxazole. So sulfamethoxazole, if you read the first slides that I have, is the one that is commonly found in bodies of water. Okay, so what we did, we put 1 milligrams of nanomaterials with 2 ml of antibiotic solution. So we set the concentration of an antibiotic solution. We set around 10 ppm. And then we mix it with 1 milligram nanomaterials. And then we incubate it with time. We centrifuge. And then we filter. And then we analyze the supernatant using spectroscopy and chromatographic method. So the material that we use YASCO 570 spectrophotometer, and then we also use Fluoromax spectrophlorimeter, and then we use the one that we have HPLC in the lab with a C8 column. Okay, so we have an Agilent 1100 unit in the lab. So the first thing that we look is in terms of the absorbance. So we have four nanomaterials. So these are commercially available. Okay, so we ordered this one. So we have aluminum oxide, silicon oxide, titanium oxide, and zinc oxide. So what we did, okay, we compare what will be the absorbance of the antibiotic solution with and without the nanomaterial. So to to make sure, okay, that we minimize some errors, we prepare the same solution of antibiotics that we mix with the nanomaterials. So as you could see here in the results, so this is the one that has no nanomaterials. So they have the same concentration as the other one. The only difference is you add them to, or you add them with nanomaterials. So as you could see here, there's a decrease in the absorbance of the doxycycline. Okay, so usually you're going to see three peaks in a tetracycline, one around 360, one at around 280, and one around 260. And as you're going to see here, the behavior of the doxycycline with the nanomaterial tells you what's happening to the antibiotics. So the reduction of the absorbance there would mean that some, okay, of the antibiotics bind with the nanomaterials, and the behavior of them differs depending on the nanomaterial that was used. So as you're going to see here, the one that has the highest reduction in the absorbance is something to do with the zinc oxide. Okay, and then you have here aluminum oxide. The one that is, we could say, less would be the silicon oxide. They're almost has the same peak. So aside from the reduction of the absorbance, you can also look for some peak in the shape like this one. So from here, it moves towards here. It moves here. So that means something is happening in the antibiotics when we mix it with the nanomaterials. So that's for the doxycycline. Now, when we try it with the oxytetracycline, this is what we have. Again, there's a reduction in the absorbance when we add or when we mix it with the nanomaterials. And that reduction is dependent on the nanomaterials that we use. Okay? And in addition to the reduction in the absorbance, there's also a shift in the peak of the material that we have. So that means something is happening between the nanomaterials and the antibiotics that we mix. And to make sure, okay, we mix both antibiotics and then mix it with nanomaterials. And based on the results, so this is just some sort of an additive effect. So it's not surprising on how it was affected. So the one that has the most change would still be zinc oxide, followed by aluminum oxide, and then titanium oxide, and then silicon oxide. And there is also, again, the shift in the peaks, okay, of the materials or of the antibiotics that was added with nano materials. So what's happened during that time? So what we could say is, since there is a difference between the absorbance of those that are mixed with nanomaterials and those without nanomaterials, so something is happening there. So the reduction of the peak could be due to some of the materials that are bound. So there's only few antibiotics that are available in the solution, okay, to have the what we call absorbance. Now, with the shape of the absorbent, it has something to do with the nature of the environment. So a pure antibiotics, it's what? Homogeneous in nature. But if you add nanomaterials there, you have a heterogeneous environment. So that results to the shape of the peaks. Okay. So we also use fluorescence. Now this is due to tetracycline being lightly fluorescent. And if we're going to look at the thing here, this is a little bit surprising, at least for the doxycycline, because as you could see in its own solution, this is the peaks that you have. But when you add it with aluminum oxide and silicon oxide, it become more fluorescent, okay, compared to the other nanomaterials that was added. So we didn't expect this to happen, but we don't really know what will happen when we did the study. Okay, so this is a good aspect because that means there might be some fluorescent materials that was formed when the antibiotics was mixed with the nanomaterials. Okay, and the same thing that happened with the oxytetracycline. So the one that has really an increase in fluorescent, there is the one that deals with silicon oxide. Okay, so the only explanation that we can have at this time is something that is fluorescent must be formed when you mix the antibiotics with the nanomaterials. Okay, and we also have the mixture that we have there. And if you're going to look at the mixture, it has the lowest uh, emission intensity compared to the one that was mixed with nanomaterials. And the one that has highest, just like in the doxycycline and the oxytetracycline on its own, is the one that is added with silicon oxide. Okay, so this is the surprising thing, the surprising part that we have in our study, and it's consistently doing that thing. Okay, now in terms of the HPLC, so what we observe here is there's two peaks that we generated from the sample, and this can be due to the two tetracyclines that we have in our sample, the doxycycline and the oxytetracycline. Now, if we're going to look at this peak, we're able to identify that this is the oxytetracycline and this is the doxycycline. So what we did is we determined the peak area of the antibiotics that are present on its own and of the antibiotics that was mixed with the nanomaterials and then filtered. Okay, and this is what we found. So for the OTC and the DC mix, so we always found that there is uh, a much higher reading because you have here a negative reduction. So this might be something to do on why they have high fluorescent. Okay, but if we're going to look at the percent reduction, DC is greatly reduced compared to the oxytetracycline. So we observe a great reduction between DC compared to OTC. And if we mix them, okay, we also seen the same, we could say, trend. The DC has a higher reduction compared to the OTC. Okay, and we found out that the reduction is much higher if you have them, okay, in mixed form, like for the one that has the zinc oxide. But that's the only thing that we have compared to the one that the thing that we have. So at least the aluminum oxide has the same performance, whether they are in mix or uh, on its own. Okay, so this is a mix and this is on its own in terms of DC. So the titanium oxide is much better if it's on its own compared when it is mixed, which makes sense because you're not competing for the binding sites. Your DC will just competing on itself. It's not competing with the OTC when you mix it with the OTC. Now for the sulfa, we also did uh, the same study as the tetracycline. Although if we're going to look at this, okay, we just finish we just completed the absorbance and fluorescence part, but we just starting with the HPLC part. Okay, so if you're going to look at here in terms of the absorbance, so SMC here, so this is sulfametacin. So some of them increase when you mix it with the uh, nanomaterials like silicon oxide and zinc oxide. Some of them will reduce when you have titanium. Some remains the same as what we observe here in aluminum oxide. For sulfametisol, okay, so sulfametisol is a 5-membered ring compared to sulfametacin, which is a 6-membered ring. So you could see the difference that we have here. There's a distinct peak that we have here. Now, when you put it with the nanomaterials, these peaks were shifted, telling you that there's a change in the environment and there's a reduction and increase in the what we call absorbance. So in terms of sulfamethisol, so if you're going to look at this, it has the highest absorbance at this peak, but when you add it with different nanomaterials, okay, so for the one with the titanium oxide and zinc oxide, it decreased, although the profile still remains the same. But if you add it with aluminum oxide and zinc oxide, the profile changes. When I say the profile change, look at the peak that is happening here. It's quite different compared to the sulfamethisol solution and the one that is added with titanium oxide and aluminum oxide. Okay, so the same thing that we could say with sulfamethoxazole. So it has something to do with the shifting here of the material. Okay, so all of them shift, and the way that they shift is not the same. Some shift at a much greater extent compared to the other. So I think the greatest one, if you're going to follow this one, is the one with zinc oxide. Okay, followed by the silicon oxide and the titanium oxide. Now for the sulfadiazine, I think this has the same trend as we have with the sulfamethoxamethacin. So two of them, okay, like the silicon dioxide and the zinc oxide increase similar to sulfametacin. And the other two has the same profile as the one as the sulfadiazine solution without any nanomaterials added. Okay, and again, we also get the spectrophlorimeter or the fluorescence that we have here. So there's a reduction that we observe in the sulfa. Okay, so here, sulfamethoxazole, those that were added with nanomaterials, they have less intensity compared to the one that is solution. But the one that we observe that's changing is around here. But as you can see, there's also a decrease here in the emission intensity. Now for the sulfametacin, this is what we get. Okay, so some increases, some decreases. So similar to the tetracycline, it's possible that some fluorescent material are formed, but the most obvious changes that we have here is this additional peak here for zinc oxide and silicon oxide. But as you could see, if you're going to look at the absorbance, those are the corresponding change that you have there. Okay. And if I'm not mistaken, this was excited at around 280 nanometer. Okay. So for the sulfamethisol, most of them increases in their fluorescent. Okay. And then for the sulfadiazine, the same thing. Some increase, some decrease. And the noted changes that we have there is the one with the silicon oxide. Okay. So in terms of the HPLC, so we just started doing this before we were hit by COVID. Okay. And what we have here is sulfamethoxazole, and we found out its retention time is around 2.80. Okay. So we found out there's a reduction when we mix the sulfamethoxazole with zinc oxide, but we're not able to calculate yet the percentage. Okay, because the students doing this left the data, and since this is not a required thesis on her, so she didn't even process the data. So somebody will continue this part among my research group. Okay, but that's the initial thing that we have on this part. Okay, so what we have the seen here that the nanomaterial has it has a good potential or a candidate in removing, if not reducing, some of the antibiotics present in aqueous solution or water-based solution. So it's the challenge now is how are you going to design them in a wastewater treatment plant, wherein you're going to put some of these nanomaterials. So how are you going to make sure that they will remain immobilized? So what will happen? Okay, you put some specialized design where you put maybe a container that has these nanomaterials, and water will pass through it, and upon passing through it, you're removing the antibiotics. You are removing what we call any antibiotic resistant genes or any antibiotic resistant bacteria on it. So that's the challenge for you on how to improve this, because the initial results that we have, it is possible, okay, that some, if not all, of the antibiotics bind with the nanomaterials. So you just need to, we could say, change the design in a way that you're going to take advantage of the nano size that it has. Okay, it's going to have a large surface area in it. Okay, so that's the nanomaterial part. Now, the electrochemical treatment, that's another part. And I think the idea for me to do this in the antibiotics, I got it when I worked there at the Department of Chemical Engineering in 2018 under Professor Bikimigo. Okay, so electrochemical treatment, they said this is another alternative that you can use to remove antibiotics from wastewater treatment. So the original idea is not antibiotic. It has something to do with some chemical waste that is produced by some plants there. Okay. So electrochemical treatment, this is another alternative process for treating various wastewater. And some example of these are electrochemical treatments: electrodeposition, electrodisinfection, electrocoagulation, electroplutation, and electrooxidation. So there are a lot, but everything has something to do with just this. Okay. the use of electricity to treat chemically. Okay, so that's the main concept that you have here. How are you going to use energy or electricity to treat a chemical? Okay, now there are advantages on using these methods. Okay, and I list them here in this slide. Now, the main advantage of using electrochemical methods is environmental compatibility. If you're going to look at the main reagent here, the main reagent is electron. Okay, there's no residues that are formed when you use electron, because what you're doing here is you're running a non-spontaneous process by applying energy. Okay, so electrochemical technique, we could say these are cleaner than physico uh, chemical techniques that are usually used. Okay, so if we're going to look at this electrochemical method that is used in wastewater treatment plants, it gives us palatable, clear, colorless, and odorless water. Okay, so in addition to environmental compatibility, it's also versatile. So many processes occur simultaneously in any electrochemical cell. So the plethora of reactors, electrical electrode material shapes, configuration can be utilized and allowed to promote different kinds of treatment technologies. Okay. So if we're going to look at the processes that work at room temperature and atmospheric pressure that we have here, so in terms of point of use production of chemicals, this is usually facilitated by electrochemical technology. So the volumes of the fluid from microliters to thousands of cubic meters can be treated. Okay. So the volume, we could say the processes work at room temperature and atmospheric pressure. And in terms of selectivity, the applied potentials can be controlled to selectively attack specific compounds. So you just adjust the potential that you apply. In terms of easy operation, it's amenable to automation. So controlled electrically and no moving parts, that's requiring less maintenance. So in terms of cost effective, it can be conveniently used in rural areas where electricity is not available, since a solar panel, okay, attached to the unit may be sufficient to carry out the process. So these are the main advantages of using electrochemical method to treat chemicals. If there is advantage or advantages, there's also disadvantages. Okay, but I think the main thing that we have here is the so-called sacrificial electrodes. Okay, so the sacrificial electrodes, they are dissolved into wastewater streams as a result of oxidation, and they need to be replaced regularly. Now, the use of electricity may be expensive, especially there in the Philippines. I think the Philippines has the second highest or the second most expensive electricity in Asia. Okay, so that would be another disadvantage. And then we have here the loss of efficiency due to the formation of impermeable oxide film. So it has something to do with the electrodes that you use. High conductivity of wastewater suspension might be required. Okay, so what happened here? This high conductivity of wastewater will be disadvantageous to a given system. And the gelatinous hydroxide may tend to solubilize in some cases. Okay, so these are the main disadvantages. But if you're going to look at the history of the use of electrochemical treatment plant. This goes a long way. Okay, so way back in 1889 in the United Kingdom, the use of electricity to treat water was first proposed. And then the application of electrolysis in mineral beneficiation was patented by Elmore in 1904. And then electrocoagulation with aluminum and iron electrons was patented in the US in 1909. So this is a 100-year-old or more than 100-year-old technology. Okay, and electrocoagulation of drinking water was first applied on large scale in the US in 1946. So electrochemical water or wastewater technologies did not find wide application worldwide then due to the relatively large capital investment and the expensive electricity supply. So that's the problem here if you venture in this method or technology. You need to have a large startup capital. Maybe that's why it's not so popular during that time. Okay, so when you have an electrochemical treatment, this is the setup that you have. So you have here the electrodes. So if you recall your electrochemistry, the Leora and the Geroa thing, so you have the anode where oxidation takes place, and you have here the cathode where reduction takes place. So what happened here? Okay, so in the anode, you have there your metal becoming oxidized. And in the cathode, you have there your charged metal, not really charged metal. We could say metal ions that is converted to metal. And each of the things that you have here, there's an associated technique: electrooxidation, electrodissolution, electroreduction, electrodeposition, and then the migration of the cation and the anion. So the way that you're going to look here, so this is where the effluent. Okay, so your sample will come here. So once it's treated, the effluent, this is where it come out, already treated. Okay, so one method that they have is this electroflotation. So it's a simple process that floats the pollutants to the surface of water body by tiny bubbles of hydrogen and oxygen gases generated from water electrolysis. Okay, so if you're going to look at the electrolysis, so there's water, there's an electron, you produce oxygen and hydrogen ion. And then there's water with two electrons, you produce hydrogen and hydroxide ion. So this was first proposed by Elmore in 1904 for the flotation of valuable minerals from ores. Flotation. Okay? So the way that you look at here, in terms of the flotation device that you have here, so you have an electrochemical reactions at the cathode and anode, and there are hydrogen evolution and oxygen evolution reactions respectively. You could see it from the reaction here. Okay, so if you're going to look at here, the gas bubble form, okay, and what happened here is some of them will float to the top of the surface. So this is the bubble. So once it forms, it goes up on top of the surface. And you have a skimmer there that remove these bubbles that produce. Okay. So an alternative to electroporation is this electrocoagulation. So this is an alternative to direct use of a solution containing the coagulant salts involving the in situ generation of coagulant by electrolytic oxidation of appropriate anode material. So you just use here an appropriate electrode. Okay, so what happened here is they neutralize the electrostatic charges on the colloidal particles and facilitate coagulation and then separation from the solution. So you have here the coagulant. Okay, and if you're going to look at the advantages of this electrocoagulation compared to the other methods, okay, it includes high particulate removal efficiency. It also includes compact treatment facility and a relatively low cost and possibility of complete automation. So if you're going to look at the electrocoagulation setup, this is how it looks like. So it's almost the same. You have here an electrodes, okay? So if you form a bubbles that floats, that's electroflotation. So if you form a coagulant, so usually it settles. You form here a sludge. And the one that you have formed there, usually foam, okay? That's your block. And if I'm not mistaken, this is the one that I learned when I was there in the Department of Chemical Engineering. So we're trying to look at the waste from the tannery, lignin industry. So we apply electricity, okay, and see what happened to that thing. Now, another electrochemical technique is electrooxidation. So this is a process in which the pollutants are destroyed or oxidized and converted into simpler forms like carbon dioxide and water. And this can be either direct titration or direct oxidation or indirect uh, oxidation. Okay, so here in electrooxidation, what you have here is the oxidation of organics present in wastewater to carbon dioxide and water or other oxides achieved into waste. Okay, first one is by direct anodic oxidation, in which the organics are absorbed at the electrode. So if you have a pollutant there, it will be absorbed and that pollutant is converted to a product. Okay, so you oxidize usually that thing. You absorb at the electrode and oxidize at the surface of the electrode. And second is an indirect one, okay, in which some oxidizing agents are generated and electrochemically they are going to be responsible for the oxidation of the organics present in the solution. So one, you have a pollutant there, okay, you allow it to be oxidized by the electrode to form a product. The other one, you allow a reaction to produce a material that will oxidize the pollutants that you have. So this is your electro oxidation. Okay. Now, during the electro oxidation treatment process, there are two types of oxidation that is possible. Okay. In one way, the toxic and non-biocompatible pollutants, they are converted in biodegradables. Organics, biodegradable organics that are further treated biologically. And in another, okay, way, the pollutants are oxidized to water and carbon dioxide, and further no purification is necessary. So in the direct oxidation, your hydroxide radicals are what we call uh, being used for complete mineralization. For indirect electrooxidation, there's chloride formation, hydrogen peroxide generation, ozone generation, and possibly the presence of a mediator, silver 2 plus. Okay. Now there are factors that affect electrochemical treatment methods. You have the current density, the electrolysis time, and anodic dissolution. pH would also play a role. Conductivity and the effect of the salts is another factor that you need to consider. And most importantly, the electrode that you use, the anode, because it's in the anode where oxidation takes place. Okay, so these are the potential of the oxygen evolution of anodes. So you have the platinum, iridium oxide, graphite, lead oxide, tin and lead alloy, titanium oxide, and silicon boron dope electrode there, and the titanium boron dope electrode. So the thing that you need to consider, the boron diamond dope electrode, okay, the BDE. Graphite is unstable, ineffective, although low cost. Platinum and iridium oxide, they're too expensive, and at some it's also ineffective. The lead oxide and tin oxide, they're unstable but easy to make. The one that is effective is the boron diamond dope. It's expensive, but it is effective. Okay, so these are just some of the process that made use of antibiotics, or they were used to treat antibiotics. Ciprofloxacin, which is a fluoroquinolone, sulfamethoxazole, okay, which is a sulfa drugs or sulfonamides, and then salbutamol. They use direct oxidation, and they use the boron diamond dope electrode there. And they found out there's a complete removal of that thing. Cephalexin, cefarotocil, cloxacillin, oxacillin, ciprofloxacin, norfloxacin. They also study that. Okay. So the way that they use here is chlorine was the one that is produced. Now you can only produce chlorine if you have a source of it. And they use here NaCl as the source, and they treated it with titanium and iridium oxide as the anode and zirconium metal as the cathode. And the efficiency of that is more than 90%. Septacidimin was also removed. So the attack of the hydroxyl radicals electrogenerated on the surface of the anode. So these are the conditions that they have. So they use CEO, cerium oxide, and a multi-wall carbon nanotube. It's 100% degradation. Okay. Now the other stuff that they have, these are not really antibiotics, some sort of a pharmaceuticals. I think the only exception is amoxicillin here. So iopramide, and this include their sulfamethoxazole and diclofenac. They use this setup, BDD, 100% removal. Ceftazidime, okay, another antibiotics. So they generate H2O2. So they use cobalt sulfite with partly graphitized carbon composites as the cathode. So they have 84% degradation efficiency. Tetracaine with hydrogen peroxide is the one that is generated. They use IRO2, iridium oxide, and ruthenium oxide together with BDD and platinum. Okay, and there's 50% of total organic carbons abatement after 360 minutes of electrolysis. So amoxicillin, you're familiar with this as an antibiotics there in the Philippines. Okay, so they generate hydroxyl radicals, and they use these different materials as electrode, and there's close to 100% degradation efficiency. Now, in the study that we use, which is really preliminary, just to let you know, we use sulfa. Okay, we use again the 6-membered ring and the 5-membered ring. And the way that we do it is we monitor the absorbance and the fluorescence, at least in some of them. Okay, so this is sulfamethoxine, So we use it varying the pH. So the pH for the acid is 3.90. The pH for the base is around 10.30. And look at what's happening. Okay. So we start with the uh, sulfamethoxine acidic solution. So this is the one that we have here. So what we do when we treated it, okay, we determine we get some samples every 20 minutes for 1 hour. So after the first treatment, this is what happens. We don't see any of the peak. And as we continue on, there's some sort of a shift in the peak here. So you hear the peak around here. So it shift around here, at least for the acidic. Now for the base, we started around here, okay? And what we did is this is the same thing. Treat it and monitor what's happening. So as you can see here, the peak, it should be around here, is almost shifting. So what complicates us is this what we call high absorbance on this part. But the one that we're after is the one on this part. Something to do with the ring. Okay. And then we also have sulfamethoxazole. So at least the peak here is a little bit obvious. But if you're going to look at the peak here, so this is the peak that we have. This is the one that we want because this is really the ring. Okay. But what happened as we treat the acidic solution, there's an obvious peak that is formed here after some time. But we're losing the peak at this time. So we're thinking that maybe the ring here is being broken and then another ring, because there's two rings that we have that are formed. We still don't know. As we say, it's more on speculation. But what we can say is there's some changes that is happening. Now for the base that we have here, so the peak shift a little bit here. And I'm not sure, but I think the change is much more pronounced in the acidic solution compared to the basic solution because I can still see some peak at that region. Okay. Now, the thing is, so that is just absorbance. So the same materials that we have, we look at the fluorescence. And we are surprised because if we just have the SNC solution at neutral pH, this is what we have. But if you change them into the acidic and basic form, they become more fluorescent. So that's one of the things that we were surprised. That's why I said, oh, maybe I can do a study on this, the effect of pH on the fluorescent. But at least that's also helped us to see what happened when we treat them. So I just show you here the 60 minutes. So from this acidic solution, okay, after 60 minutes, there's a decrease in the fluorescent material. The same thing with the one that is base, although the one in the base is really pronounced because there's a shifting of the peak toward this thing. So that's for the sulfamethoxine. Now for the SMX, okay, so what happened here, I think my students forgot to get the peak of just the base and the acid, okay? We're still doing this one when the pandemic came in. So this is the MX solution, so it increased, but we're not able to compare what's the initial SMX. I think it was there. My student wasn't just able to send me the data that I have. But the thing that we have here, based on the initial finding that we have, this is of great potential in removing antibiotics in the uh, wastewater treatment plant. Now, the thing that we want to do is we're looking for something that has an LCMS and try to see if there are changes in terms of the composition when you treated the antibiotic solution, whether it is an acidic or basic solution. Okay. So the main conclusions that I have here, or we could just say conclusion, that both the use of nanomaterials and electrochemical methods has great potential in the removal of the antibiotics in environmental samples. Maybe my challenge to you is how are you going to make this into a large scale method? Because what we did is just the beaker scale thing. So I know engineering is for you to transfer what you've done in the lab into a design or into what we call the plant. And maybe that will be part of the question that you are going to answer in this part of my presentation. So I would like to thank you for your time. I would like to thank Ma'am Migo for allowing me to share the knowledge that we have that I have, although I gained some of this knowledge from her and the Department of Chemical Engineering there in SEAT. And before I end this lecture, I would like to thank the students who did this study. So Hilary Juper, so he did most of the nanomaterials, okay? And then he's an MS Environmental Science student who just finished his MS last summer. And then Gwen Ayanoni, okay, the BSc student who validates Hillary's result in the nanomaterial part, and Gwen started to do the electrochemical uh, part. So I think without them, I don't have any data to present to you. So thank you very much. Okay. I hope you learned something. So magandang araw, magandang umaga, magandang hapon, or magandang gabi saan man kayo dyan sa Pilipinas. Maraming salamat po.